Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so let's start. So it's a great pleasure to present Charlie Fefferman. I mean, I probably don't need to introduce him. One of my greatest heroes and probably one of the greatest analysts ever. And he will talk to us about extending CK functions, things around that. Thanks a lot.
Thank you, Asaf. Well, that's one of the more flattering introductions. Okay, I sure hope that none of you heard my talk at San Antonio, because this is more or less an isomorphic copy. Maybe if you did, you should leave now. Okay. All right, so this has been my obsession for the last few years. The problem has a finite flavor and an infinite flavor. I started with the infinite flavor. The infinite flavor goes back to an old problem posed by Whitney in 1934. The finite flavor, which I've been obsessed with lately, is joint work with Bo'az Klartag, whom I think, am I right, everybody here knows Bo'az? Shall I write his name on the board? Let's write his name on the board. Okay, let me first just describe the infinite flavor of the problem. Then I'm going to tell you what the results, well, all right, so I'll describe the infinite flavor of the problem, then the finite flavor of the problem, then I'll state the results on the finite flavor of the problem, and then let's have a little democracy. I just wonder whether people would like to see how the finite results are proven, or instead I could state the infinite results. So we could have this sort of nice, pleasant talk with statements of theorems and no proofs. Okay. I'm sorry?
I want a proof.
You want a proof? Okay. All right, so let me state the infinite problem. All right, so the infinite problem is this. So we're given positive integers m n bigger than or equal to 1, and they're going to be fixed throughout all the problems and all the theorems, and we're going to work with Cm of Rn. Okay. Now, and so let's say if I have a function f, this means the Cm norm, and the fact that I write it means that I'm asserting that f is in Cm. Okay, let's say if f is not in Cm, even if it has bounded derivatives or something, this is identically infinite. Okay, fine. So Whitney's problem is this. Suppose, so this sits in the background, and now suppose I'm given some completely cockeyed set E contained in Rn. It could be either completely arbitrary or it could be compact but completely arbitrary. That doesn't matter. Okay, and then I'm given some real valued function, little f, defined on the set E. There. Okay, now Whitney's question is the following. We would like to extend little f to a Cm function. So, and that may or may not be possible. Whitney's problem is to decide whether there exists a capital F in Cm of Rn such that f equals f on E. Okay, so what kind of calculations can you do in principle that will be necessary and sufficient for this? But again, the point is that you assume nothing about E. All right, that's Whitney's problem. All right, now here's the finite flavor of Whitney's problem. Okay. Suppose that instead of an arbitrary infinite set, I give you some arbitrary large finite set. So think of a lot of points in this room. Okay. Now I want to find the graph of a Cm function so that that graph passes through, or maybe passes close to, all of those points. Now, of course, I can do that, given any function defined on a finite set. Of course, there is a CM function that agrees, but the problem is to minimize the CM norm, or in any event, to minimize the order of magnitude of the CM norm. Now, all right, so let me pose the problem a little bit more precisely, and I'm going to try to focus in on it. Okay, I'm going to start. So the initial version is just the vague thing that I said. Now let's get a little more precise. Okay, so the m and n again are fixed. This time E is in Rn, but it's finite, and the number of elements of E is, let's say, capital N. So I'm going to think of these guys as fixed and this guy as arbitrarily big. Okay, and I don't know where, I mean, once you show me these points, I know where they are, but I don't want to make any assumptions about their geometry. Okay, all right, fine. Now I'm given a function f from E to R, and that's the function, I mean, that gives me points in Rn plus 1. Think of little n being 2, and the graph of this function, little f, will be the points in the room. Okay, now, close to, right? The function is supposed to pass close to these. How close is close? Well, I'm going to introduce another function, sigma, which maps E to the non-negative reals. Okay, and this is going to be my tolerance. If I demand that capital F should exactly agree with little f on E, that corresponds to setting this function sigma equal to 0. Okay? All right, so now the problem is, well, wait, all right, before I state the problem, so let me make a definition. All right, given all that stuff, what we're going to do is look for pairs, a function f in Cm, and a positive real number m, such that two things happen. First of all, the norm of f is no bigger than m. And secondly, big F minus little f is less than or equal to m times sigma of x for all x in E. Okay? Or maybe all but a few. Okay?
Since n is finite, you have to tell us what a few is.
It's true. You know what? I'll come to this later. I'll come to this later. For the moment, yes. So for the moment, let's say that's the definition. All right, that's what we're looking for. You might wonder why the capital M should be there, but I haven't told you at all what the sigma is. So if you don't like the M there, your sigma will be, my secret sigma will be 1 over m times your sigma or something, and so that doesn't really matter. All right, so we're looking for such things, and I'm going to define this quantity, norm f E sigma, and that's simply the inf over all m, such that there exists f with those properties. Okay? So, those are definitions. Now let me give you vaguely stated problems, and then I'll give you some more definitions that will have the effect of stating precisely the problem. All right, so vaguely stated problems, I'd like to pose 3 problems. Problem 1, given EF sigma, okay, compute the order of magnitude of this number. I'd be thrilled to be able to compute the number perfectly. I can't do that. I think it's probably very hard. Compute the order of magnitude of this number. Problem 2, so that amounts to finding the best m. Problem 2, compute a function capital F such that this is true with m being roughly as small as possible, having the smallest possible order of magnitude. Okay, compute such an f. And of course, one of the definitions I have to give you is what does it mean to compute a function f? Okay. Problem 3, all right, now what does a few mean? Suppose that I give you EF sigma, and I also give you a number z less than or equal to n. Now imagine that I am allowed to take my set E, I'm allowed to take this problem, and I'm allowed to remove any z points. Okay? Now figure out how small I can make this norm so I'm interested in the minimum of this quantity f, let's say E minus S sigma over S contained in E with at most Z points. Okay? And the third problem is compute the order of magnitude of that and figure out which set to remove. All right. Now these problems are all hard, but slightly fudged versions of these problems turn out to be solvable by very efficient algorithms. I mean, in the sense of theoretical computer science, and I don't claim that anything is practical.
Now, one naive solution is sort of splines, right, or spleens.
Yes. So a solution will turn out to be a piecewise polynomial, a spline. Yes. Okay. Now, all right. Let's see. Right. So now various words. Order of magnitude. For purposes of this talk, here's what order of magnitude means. I've got these two numbers, m and n greater than or equal to 1, which are supposed to be fixed. Okay? Suppose, whenever I write a constant, let's say if any constant that's called c means simply a constant depending only on m and n. Okay? And now suppose that I give you, let's say, these data. And from them I calculate two non-negative numbers, x and y. I'm going to say that these two numbers have the same order of magnitude if each one is less than or equal to c times another, where c depends only on m and n. Okay? That's what I mean by two things having the same order of magnitude. So of course, depending on the value of c, this may or may not be practical. But nevertheless, right. So x and y have the same order of magnitude if cx is less than or equal to y is less than or equal to cx, where these things depend only on m and n. And to compute the order of magnitude of x means to compute some y such that x and y have the same order of magnitude. Okay? So that's what order of magnitude means. Now let's see, what does it mean to compute a function? Here's what I have in mind. Okay, we sit at a computer, we enter the data, EF sigma and maybe Z. Let's not worry about Z until later. We enter EF sigma. Okay? The computer grinds along for a while and then sends us a message, I'm ready. Okay, now that it's sent that message, we can query the computer. A query consists of a point x in space, and the response that the computer has to give us is, let's say, the function value and the derivatives up through order little m, because after all, this function is supposed to be m times differentiable. So we address a query. The query consists of a point. The computer answers the query. The answer consists of the function value at that point together with the derivatives up to order m at that point. Okay, that's so that's what I mean by computing a function. And now we can do either a good, efficient job or a lousy job, depending on three things. First of all, there's the one-time work, right? How long does the computer grind along before it signals, I'm ready? How many operations? Okay. Secondly, how long does it take to answer a query once it's done the one-time work? And thirdly, what's the storage required by the computer? So those are the three numbers we need to keep track of in order to say whether we're doing a good job. Okay, let's see. The next thing to say is, all right, computer. What's a computer? This is supposed to be theoretical CS. Let me just say 2 or 3 words. Well, 1 minute about what's a computer. I don't want to get involved in questions of parallel computation, although a lot of stuff is happening in parallel, and presumably this. Never mind. We have a von Neumann computer. Okay. Now. I would, for purposes of this talk, I would rather not worry about round-off errors. And so I'm going to pretend, for purposes of this talk, that the computer can deal with exact real numbers, and that at one location in RAM, an exact real number can be stored, and 2 exact real numbers can be multiplied perfectly, and so on. This leads to problems that are very well known to theoretical computer scientists, although I wasn't aware of them until Bo'az explained them to me. And so we have gone back and redone the analysis and we are lucky in that for these problems, there's a rigorous analysis of the Roundoff error, and there's a version of all this stuff for computers that deal with finite precision real numbers. Let's not worry about that now, okay? All right.
As long as you don't do, as long as you only do addition, multiplication, and stuff, it doesn't really need to
do a little bit more than that. We need greatest integer functions and powers of 2. I mean,
so it does lead to problems.
Potentially it could lead to problems, and therefore we worked extra hard and got the rigorous analysis of the Roundoff error. Okay, so let's see, that's what a computer is. So let's see, I think now I've specified the problem, right? So, oh, there's one important thing I want to say that I haven't said yet. I want algorithms that always work. If you make assumptions, let's say that sigma is 0, for example, and the geometry of E is favorable, E is something like a lattice in space or anything like that, this problem becomes much, much easier. I'd just like to show you one example of a delicate case. Okay, so let's erase some stuff. Okay, let's suppose that there's some low-degree polynomial. Low means lower. I mean, if we're dealing with CM function, then polynomials of degree less than m are low-degree polynomials. Okay, and what I've drawn here, this curve is supposed to be the set where q equals 0. Okay, now let's say that I'm not going to tell you what the function little f is. Let's say that the sigma, the tolerance, is equal to 0, so I want to match the little f exactly on the set E. And let's say the set E consists of the blue dots. Okay? Now, so I'm trying to compute a function that agrees with some given function exactly on the blue dots. So we know the value on the blue dots, and we're trying to figure out what the function is. And so let's say we have a dumb algorithm, and it tells us that our function is f. Well, we could ask, is the dumb algorithm wrong? And in fact, is the answer f plus q? Maybe sigma is not 0, but it's very small. If, I mean, after all, the polynomial q is very small on the blue dots. And so we could easily be fooled into saying one of these when the correct answer is the other. Now, you could think that it doesn't matter, that one works just as well as the other. But in fact, at most one of these can be right because of exactly the way I drew these dots. And this little example gives a hint of the spirit of the whole thing. Okay, so look at these two blue dots and draw a line through them, a straight line. Now that straight line makes a not so small angle with the curve. Okay, now if I tell you to very good accuracy what my function value is at the two blue dots, I have a very good idea of what the directional derivative of the function is in the direction of the line. Now let's look at this, let's say at this blue dot. Well, this blue dot is pretty close to these two, and therefore it's a pretty safe bet that the directional derivative of the function, whatever it is in this direction, is close to the directional derivative of that, which in turn is close to that difference quotient. And therefore we have a good idea what the difference, what a directional derivative is of our desired function in that direction. And on the other hand, if you compare f and f plus q, at least one of them is quite likely to have not at all the right directional derivative in that direction transverse to the curve. So information is being passed. This point looks at that point and says, aha, not only do I know a function value, but I know a directional derivative. And this point looks at this point and says, aha, the direction, I know something about the directional derivative there, therefore I know something about my own directional derivative. And so messages are being passed from point to point. Okay. So that's an example of a delicate case. Okay, now let me think. Have I now said enough to state the theorems? I think so. All right. So let me just state theorems about what can be done.
Why is it so delicate? You just said Q, but you didn't say that Q prime is the Alex's curve from one side.
Well, wait. So if I'm sorry. So if Q and Q prime are, let's see what to say. I'm sorry. I didn't say that Q prime is small, but that's the problem.
But to some extent, I don't quite understand. Given that we want to match derivatives, I don't
right.
really see why you said, oh, F plus Q should be as good.
Okay. F plus Q is as good if you are sloppy.
And forget that you should actually.
And forget that you should actually match derivatives. Okay? Okay. No, I don't. I mean, all right. All right. I think. All right. I think the facts that I've stated are clear, and the interpretation of the facts that I've stated is a matter of, I don't know, spin. Let's not get into it. Okay. All right. So let me state the theorems. So the bottom line is that until you get to this problem with the z outliers, there are what look an awful lot like optimal results. Okay. So first of all, given, well, again, m and n just sit there in the background. They're always given and fixed. Okay. So given E F sigma with E having n points, we can compute the order of magnitude of this F E sigma using n log n operations and storage. Okay. Now, of course, the storage is comparable to what's needed to state the problem. That's got to be optimal. Here, let's see. Well, n, I mean, except for the log n, n is what's needed to read the data. I don't know what, I mean, I'm ignorant of theoretical computer science. Let me just say I would be very surprised if you could get rid of the logarithm. Okay, so that's how well we can compute the norms. Now, let's see. How about computing a function, computing an f that works with an optimal m? So we can compute an f that works with m of optimal order of magnitude. Again, no hope of getting v best. I don't even know if there is a v best. Maybe it's an inf and not a minimum. But there we can compute an f like this in the sense that I described the dialogue with the machine, and the one-time work is c n log n. The work to answer a query is c log n, and the storage is cn. So again, that looks optimal. I mean, except for logarithms, it's obviously optimal, and I would be surprised if you could get rid of the logarithms.
So maybe many steps which are consistent with the data in this respect.
Oh yes.
So do you know something about how they differ from each other?
Oh yes. So for instance, here's another question. Okay, suppose that I give you some point in space, not necessarily one of the data points, but possibly one of the data points, and I make and I make some space of, think of the space script p of all m minus first degree polynomials, or if you like mth degree polynomials, it doesn't matter. You could ask, let's say, so for every capital F that works with a given m, I could look at its Taylor polynomial, and I could make the set of all Taylor polynomials of f's that work with such a given m, and I would get, associated with this given dot, I would get some convex set in the vector space P. Then once you've done the one-time work, another thing you can do is that given a query point x in time log n, you can essentially compute this convex set up to what? Well, I mean, you can compute some ellipsoid, which is essentially equivalent to this convex set. So that's an example of the statement that, yes, one has good control over what all possible capital F's are. Okay?
Do you have some good estimate on the diameter of this set?
It depends completely on the geometry of, you can read it off from the query. Okay.
And if you do the discrete thing, you get extra logs.
I'm sorry, if you do the, I'm sorry.
You take into account the rounding errors, you get extra logs.
No, so it depends. So it depends now on how you count. Right, so your question is, let me make sure I understand your question. Imagine you're allowed to make.
Bits and not.
Oh, then of course the storage space is measured in numbers, and so if a number takes s bits, then you multiply the storage by s. Okay, and time work, it's the number of operations, and so if you're working on s bits, it takes what, s log s bits to do. I mean, it takes s log s work to multiply two numbers, and so it's a matter of accounting. Okay.
The order of norm f's of these things to a constant.
Right.
Do you have a sense for whether the constant is a polynomial size in M and N, or whether it's bounded by some predictable function of M and N?
Right. Okay. These constants are, these constants are much too large to be practical in our implementation. I would be interested to know. I would be interested to know whether one could do better. Now, we showed no interest in optimizing the constants. It's clear one can do better, but whether one can get reasonable constants, I don't know, and that would surely take substantial additional ideas at a minimum. Let's see. But nevertheless, they're primitive recursive. I mean, they're at worst multiply exponential. Okay.
You refer to them as constants. How badly do they grow with M and N?
I think that was the question. They're multiply exponential in little m and little n if you just follow our proof.
So it was a tower.
Oh, not even a tower. I mean a fixed number of exponentials. So I think triply. So let's say just to be safe, let's m plus little n raised to the power little m plus little n raised to the power little m plus little n. That's probably good enough. Okay, something like that. So very far from practical, but.
But n equals 3, m equals 2. That's already interesting.
Yes, thank you. Actually, thank you. Okay, so. Yeah. Right. I should say, so I'm just stating the theorems. I haven't said what was known and what wasn't known. I think, I mean, you're the expert, I'm not. I think that these questions are trivial cases of known things when little m is 1. But as you say, little m equals 3 and little n equals 2 that wasn't known. Okay, thanks. All right. Now let's bring in the outliers. Okay, so let's bring in this z. So the question, the way I stated it, I don't know how to. I don't know how to say anything. But if you just make the question a little bit sloppier, then it can be answered pretty well. Not optimally, but pretty well. So let me state the next thing. Okay, so now given. So again, m n greater than or equal to 1, fixed. And now we're given E, F, sigma, and Z with E having endpoints, and Z, let's say, between 1 and n. Okay? So what we're going to do is we're going to compute a set S. Well, let's call it S star. That's the set we like. And it's going to have the following properties. First of all, so it's contained in E. So first of all, the number of points here is no bigger than a constant times Z. Okay, so maybe it doesn't have, maybe we're not throwing out Z points, which we wanted to do. Maybe we're throwing out, well, we are throwing out as many as C times Z points. But for any competing S with at most Z points, okay, so notice, of course, this is not quite a fair competition. S star has more points than S is allowed to have, but not a whole lot more. Okay, so for any such, we have F of E minus S star sigma less than or equal to a constant times F E minus S sigma. Okay, so in other words, this S star is not optimal, but it is at least not possible to get a much better norm with a much smaller set. Okay, so in that sense, it's sort of optimal. Okay, now this can all be done with work C, Z, n log n, and storage C, n. So of course the storage is optimal. I don't know what, I mean, I would be very surprised if the work is optimal. I really think it can be improved. But nevertheless, it's polynomial. Okay, and of course, I mean, I don't have to tell you the number of sets you would have to look at is n choose z, which is not polynomial. It's a big number. Okay, so those are the results for the finite problem. Well, there are other results, but I think that's enough to give the picture. Let's see. How long do I have? Maybe 20, 25 minutes?
Yeah.
Okay. Okay. So let's see. I could do one of two things. I could explain the infinite flavor of the problem, or I could tell you a little bit about how the algorithms work. Shall I flip a coin or take a vote? What shall I do? Algorithms. Okay. All right. Let me state a theorem which hides most of the work, but at least which explains how you do the outliers. Okay. And once you believe the theorem, then it's easy to take care of outliers this way. But again, there's no reason to believe that this is optimal. All right. All right. All right. So suppose that I'm fixing my m and n, and I give you the E and the sigma, but I hold back on the F. I don't yet tell you what the F is. Okay? Then there exists a list of subsets. Let's call these subsets S1, S2, SL, contained in E, with the following properties. So first of all, each one of these subsets is little. Okay. Secondly, there aren't too many of them. So the number of them is this capital L, and that's less than or equal to a constant times n. Okay, so there are about as many subsets as there are points. And the third point is that for any f, for any f mapping E to R, you can measure the order of magnitude of f E sigma by just looking at the maximum over all of these little subsets of F SL sigma. Okay. Now, I don't want to get into trivial details, but the fact is that if a set is rather small, if a set has at most a bounded number of points, then it takes at most a bounded amount of work to calculate at least the order of magnitude of this number. The whole issue is how things grow with the number of points or the. All right. So
the new thing over your old stuff is B, right?
Yes.
Okay.
Yes. And
Yeah.
D, which is about to be written. Okay. No. Okay. So the new thing over the old stuff is B, but also D. So
If you just give a polynomial, then you don't need B.
I'm sorry if you just care.
What polynomial you mean? Because it's bounded size.
Right. So the old. Well. Right. Okay. Right. And the last thing is that the list S1, SL can be computed with work Cn log n and storage Cn. Okay. Suppose you believe that. I would just like to show you how it then becomes trivial to remove outliers. Again, maybe it's non-trivial to do an optimal job, but at least to do what I said we could do. It becomes easy once you believe this. Okay, so let me just make a little remark. So suppose that we're given M, N, and E, F, sigma, and Z. Okay? I have to find a set S star star that essentially wins against all competitors as before. And the remark that I want to make is that the competitors I'm worried about are subsets S with the following property. Okay, let's say the precise meaning of that is that this is less than or equal to that times a sufficiently small constant depending only on little n and little n. If capital S doesn't do this, then I gain no advantage by removing it, so I don't need to think about it. Okay. Now, given that, then here's the algorithm. So I want to, all right, given EF, sigma, and Z, I want to produce at most C times Z points, and I'm going to call those points S star. Okay. What do I do? Well, let's see. First thing I do is I check whether I'm in a trivial case. Is E empty or is Z equal to 0? And if that's true, there's nothing to do. Okay. Otherwise, see, I read page 1 of a computer book. Okay. Now, if there is something to do, then the next step is you go ahead and, according to part D, you generate this list of subsets. Okay. And so you can compute at least the order of magnitude of each of these. Take the biggest one. Throw away the corresponding S sub L. Once you've thrown it away, you are in the same situation as before, except with E replaced by E minus the stuff you threw away, and with Z replaced by Z minus 1. Why does that work? There's one little simple observation. Namely, all right, so let's say we've picked L star, let's say, maximizes. I mean, I'd like to say that it maximizes this, but I can't quite do that. I can only compute the order of magnitude. But for each L, I compute a number which has the same order of magnitude as this thing, and then I pick L star to maximize that number that I've computed. Okay. And the point is simply that if S is an interesting set in this sense, then at least one, then S must have at least one point in common with S sub L star. Okay? Should I write that down, or is it just obvious? I've managed to pose the question in such a way that the answer is yes, no matter what. Should I write anything down? Okay. So so that's how so that part of the problem is easy, and every time you remove C points, and therefore one point of the set S, every time you do that, it takes work n log n. So you do it Z times. It takes all right. The work is as described, and the algorithm is probably pretty dumb. Okay. Anyway, now how to prove the other theorems. So how do you start thinking about the problem? And the answer is that well, all right. So let me ask yet another question, and this is the question that you start to answer. And thinking about this question leads you in the right direction. Okay. So and in fact, it's the question previously posed. So well done. So if there exists f such that the norm of f is less than or equal to m, and f minus f is less than or equal to m sigma of x, all x in E, then what can you say about, let me call it J, the jet, Jx0 of f. So what I mean by this is simply the mth or the m minus first order, actually the m minus first order Taylor polynomial of f at some given point x0. Okay. Well, let me just define, all right, let me define a convex set, gamma of x0 m. And that's simply by definition the set of all possible Taylor polynomials at the given point x0 for functions f with this property. All right. So by definition, Jx0 of such an f belongs to that. And this thing sits inside that vector space P of all polynomials of degree m minus 1. Okay. Trivial point from elementary analysis. Suppose, let's say you're in a car, and the car can accelerate at most 50 meters per second per second. I don't know whether that's a realistic order of magnitude, but let's say 50 meters per second per second. Then, and I tell you where the car is perfectly every trillionth of a second. What can you say about the acceleration of the car at a particular instant? And every second, I'm sorry, so every trillionth of a second I tell you exactly where the car is, and the car is capable of acceleration of at most 50 meters per second per second, then what can you say about the acceleration at a given time? And the answer is, all you can say is it's at most 50 meters per second per second. That's it. Okay? So that's why I'm not interested in the highest order part of the Taylor polynomial. You can say basically nothing about it that isn't completely trivial from that. The non-trivial information all concerns the lower order jets. Okay. So, but now what we're going to do is we're going to try to compute these guys. Now we're not going to try to compute them exactly. We're going to try to sort of, we're going to compute their approximate sizes and shapes. Let me not make precise definitions, but for example, for a fixed m, if it looks like this, and I tell you that it looks like that, and these two sets, each of these two sets is contained in a fixed dilate of the other or something, I declare that I'm happy. Let me not get into precise definitions. All right. Now, what do you do? Well, what I'm going to do is define a family of convex sets. So first, let's say that for the moment I'm only interested in x0 in E. Although the question is interesting when x0 is not in E. What to compute this thing. So suppose that x0 is in E. For each integer L greater than or equal to 0, I'm going to construct for you explicitly a convex set like this. Okay? With the property that this convex set obviously contains that one. I'm going to construct it by induction on L. Okay? And the construction is such that this thing can be computed. But then there's a theorem that after you've done this construction enough times, as L increases, these sets are going to get smaller. The inductive step is to cut down on the gamma. Okay? And after you've done this construction enough times, this gamma that you end up with is guaranteed to be comparable to that gamma. Notice that already that tells you enough information to decide, for instance, the order of magnitude of the best CM norm. Because after all, so that, for example, is there a function, for a given m, is there a function that does this or not? If there's no function that does this gamma is, guess what, the empty set. So simply you ask, is gamma the empty set? If you can compute the approximate size and shape of a convex set, you can decide whether it's empty. And if it's empty, then there is no function. And if it's non-empty, then there is a function. Okay? So the information is there. All right. Okay. So what's the construction of these gamma L's? Well, let me tell you the two trivial pieces of the induction. So there's the case L equals 0, and there's the induction step. All right, so let's do the case L equals 0. All right, so gamma of x0, comma 0m is the following set of polynomials. Remember, that's the space of all possible Taylor polynomials. It's the set of all these that do two things. First of all the derivatives at the point x0 are less than or equal to m. Okay, and p of x0 minus f of x0 is less than or equal to m sigma of x0. Okay? Now, if there exists a function capital F with all these properties, its Taylor polynomial at the point x0, guess what? Satisfies that because the CM norm is not so big, and satisfies that because capital F does what it does, right? So that's nothing. It's trivial that the real gamma that we want contains this guy. Okay? All right, let's do the induction step. So, well, let me make first a little remark in order to do the induction step. Okay? So the little remark is this. Suppose that the norm of F is no bigger than m. Okay? And suppose I give you 2 points, x0 and y0. And let's say p is the jet of this function f at x0, and q is the jet at y0. Okay? Then the remark is that p is close to q if x0 is close to y0. That's obvious, and the exact statement is this. Okay, that's Taylor's theorem. So armed with that deep fact, we're going to do the induction step. Okay, so now suppose suppose we're already given gamma of x0 Lm for all x0 in E. All right, we're going to define gamma of x0 L plus 1 m for all x0 in E. And here it comes, okay? So gamma of x0 L plus 1 m equals set of all p such that for any y0 in E, there exists q belonging to gamma of y0 L and m, which we already know about, such that Taylor's theorem happens. Now, because of Taylor's theorem, if we're guaranteed that the jet of f at every point belongs here, then also the jet of every point belongs here. Notice this guy is contained in that guy because, for example, we could take y0 to be x0, and then this would say that q is equal to p, and yet it belongs. This guy is trivially a subset of that guy. And if it hadn't been, if nature had been so malign, then we just would have intersected them together and declared that to be the next one. So that's one step of the induction. Now that's not really one step of the induction because it's too expensive to compute. For each x0, you have to look at all y0, and so the number of operations is n squared. And so you do something clever. So I was unaware of how to make clever computations, but Bo'az explained it to me. And so this is not really the definition of gamma, but the real definition of gamma is a lot like this, but smarter.
So it's not the same set?
So it's not the same set. It's not that there's some clever way of computing this set. It's a different set. But you crank this machine a bounded number of times, and there's some number L star, not the previous L star, but there's some number L star depending only on little m and little n, such that by the time you're finished, the gamma of x0 L star m is guaranteed to be essentially that. And that's true not just for this procedure, but also for the cleverer one, and in fact for the way the thing actually works. There are various properties of these families of convex sets gamma, which you can prove by a trivial induction. And then there's a theorem that says that if you have any family of convex sets with those formal properties, then it follows that for L star, this constant, that in fact the convex set that you compute is essentially that one. That theorem is, as far as I can tell, is a really hard theorem. Okay, we worked hard. There is no simple proof. The statements of the results show that the problem is easy. Okay, the proof doesn't look easy. At this point, having labored long and hard on a machine, I'm in love with the machine, so I'm the wrong person to simplify this, but I think it cries out to be simplified. Let me just mention one problem that I would love to be able to do and have not even really started to think about. So far, always the problem has been to find the graph of a function. But I would love to find algorithms that deal with, let's say, embedded CM smooth surfaces, which are not necessarily the graphs of functions. Let me not say anything more about that since I don't know anything about it. This is a reasonable place to stop. Thanks.